Tidal acceleration is an effect of the tidal forces between an orbiting natural satellite and the primary planet that it orbits. The acceleration causes a gradual recession of a satellite in a prograde orbit away from the primary, and a corresponding slowdown of the primary's rotation. The process eventually leads to tidal locking, usually of the smaller first, and later the larger body. The Earth-Moon system is the best studied case. A similar process of tidal deceleration occurs for satellites that have an orbital period that is shorter than the primary's rotational period, or that orbit in a retrograde direction. The naming is somewhat confusing, because the speed of the satellite relative to the body it orbits is decreased as a result of tidal acceleration, and increased as a result of tidal deceleration. Earth-Moon system. Discovery history of the secular acceleration. Edmund Halley was the first to suggest, in 1695, that the mean motion of the Moon was apparently getting faster, by comparison with ancient eclipse observations, but he gave no data. In 1749 Richard Dunthorne confirmed Halley's suspicion after re-examining ancient records, and produced the first quantitative estimate for the size of this apparent effect, a centurial rate of +10 in lunar longitude, which is a surprisingly accurate result for its time, not differing greatly from values assessed later, e.g. in 1786 by de Lalande, and to compare with values from about 10 inches to nearly 13 inches being derived about a century later. Pierre-Simon Laplace produced in 1786 a theoretical analysis giving a basis on which the Moon's mean motion should accelerate in response to perturbational changes in the eccentricity of the orbit of Earth around the Sun. Laplace's initial computation accounted for the whole effect, thus seeming to tie up the theory neatly with both modern and ancient observations. However, in 1854, J.C. Adams caused the question to be reopened by finding an error in Laplace's computations. It turned out that only about half of the Moon's apparent acceleration could be accounted for on Laplace's basis by the change in Earth's orbital eccentricity. Adams's finding provoked a sharp astronomical controversy that lasted some years, but the correctness of his result, agreed upon by other mathematical astronomers including C.E. Delaunay, was eventually accepted. The question depended on correct analysis of the lunar motions, and received a further complication with another discovery, around the same time, that another significant long-term perturbation that had been calculated for the Moon was also in error, was found on re-examination to be almost negligible, and practically had to disappear from the theory. A part of the answer was suggested independently in the 1860s by Delaunay and by William Ferrel. Tidal retardation of Earth's rotation rate was lengthening the unit of time and causing a lunar acceleration that was only apparent. It took some time for the astronomical community to accept the reality and the scale of tidal effects, but eventually it became clear that three effects are involved when measured in terms of mean solar time. Beside the effects of perturbational changes in Earth's orbital eccentricity, as found by Laplace and corrected by Adams, there are two tidal effects. First, there is a rear retardation of the Moon's angular rate of orbital motion, due to tidal exchange of angular momentum between Earth and Moon. This increases the Moon's angular momentum around Earth. Secondly, there is an apparent increase in the Moon's angular rate of orbital motion. This arises from Earth's loss of angular momentum and the consequent increase in length of day. Effects of Moon's gravity. Because the Moon's mass is a considerable fraction of that of Earth, the two bodies can be regarded as a double planet system, rather than as a planet with a satellite. The plane of the Moon's orbit around Earth lies close to the plane of Earth's orbit around the Sun. rather than in the plane perpendicular to the axis of rotation of Earth, as is usually the case with planetary satellites. The mass of the Moon is sufficiently large, and it is sufficiently close, to raise tides in the matter of Earth. In particular, the water of the oceans bulges outwards and away from the Moon. The average tidal bulge is synchronized with the Moon's orbit, and Earth rotates under this tidal bulge in just over a day. However, Earth's rotation drags the position of the tidal bulge ahead of the position directly under the Moon. As a consequence, there exists a substantial amount of mass in the bulge that is offset from the line through the centers of Earth and the Moon. Because of this offset, a portion of the gravitational pull between Earth's tidal bulges and the Moon is not perpendicular to the Earth-Moon line, i.e., there exists a torque between Earth and the Moon. This boosts the Moon in its orbit and slows the rotation of Earth. As a result of this process, the mean solar day, which is nominally 86,400 seconds long, is actually getting longer when measured in SI seconds with stable atomic clocks. The small difference accumulates over time, which leads to an increasing difference between hour clock time on the one hand, and atomic time and ephemeris time on the other hand. See delta T. This led to the introduction of the leap second in 1972 to compensate for differences in the basis for time standardization. In addition to the effect of the ocean tides, there is also a tidal acceleration due to flexing of Earth's crust, but this accounts for only about 4% of the total effect when expressed in terms of heat dissipation. If other effects were ignored, tidal acceleration would continue until the rotational period of Earth matched the orbital period of the Moon. At that time, the Moon would always be overhead of a single fixed place on Earth. Such a situation already exists in the Pluto-Charon system. However, the slowdown of Earth's rotation is not occurring fast enough for the rotation to lengthen to a month before other effects make this irrelevant. About 2.1 billion years from now, the continual increase of the Sun's radiation will likely cause Earth's oceans to vaporize, removing the bulk of the tidal friction and acceleration. Even without this, the slowdown to a month-long day would still not have been completed by 4.5 billion years from now, when the Sun will probably evolve into a red giant and likely destroy both Earth and the Moon. Tidal acceleration is one of the few examples in the dynamics of the solar system of a so-called secular perturbation of an orbit, i.e. a perturbation that continuously increases with time and is not periodic. Up to a high order of approximation, mutual gravitational perturbations between major and minor planets only cause periodic variations in their orbits. That is, parameters oscillate between maximum and minimum values. The tidal effect gives rise to a quadratic term in the equations, which leads to unbounded growth. In the mathematical theories of the planetary orbits that form the basis of ephemerides, quadratic and higher-order secular terms do occur, but these are mostly Taylor expansions of very long-time periodic terms. The reason that tidal effects are different is that unlike distant gravitational perturbations, friction is an essential part of tidal acceleration, and leads to permanent loss of energy from the dynamic system in the form of heat. In other words, we do not have a Hamiltonian system here. Angular momentum and energy. The gravitational torque between the Moon and the tidal bulge of Earth causes the Moon to be constantly promoted to a slightly higher orbit and Earth to be decelerated in its rotation. As in any physical process within an isolated system, total energy and angular momentum are conserved. Effectively, energy and angular momentum are transferred from the rotation of Earth to the orbital motion of the Moon is converted to heat by frictional losses in the oceans and their interaction with the solid Earth, and only about 1/30 is transferred to the Moon. the Moon moves farther away from Earth, so its potential energy increases. It stays in orbit, and from Kepler's third law it follows that its angular velocity actually decreases. So the tidal action on the Moon actually causes an angular deceleration, i.e. a negative acceleration of its rotation around Earth. The actual speed of the Moon also decreases. Although its kinetic energy decreases, its potential energy increases by a larger amount. The rotational angular momentum of Earth decreases, and consequently the length of the day increases. The net tide raised on Earth by the Moon is dragged ahead of the Moon by Earth's much faster rotation. Tidal friction is required to drag and maintain the bulge ahead of the Moon, and it dissipates the excess energy of the exchange of rotational and orbital energy between Earth and the Moon as heat. If the friction and heat dissipation were not present, the Moon's gravitational force on the tidal bulge would rapidly bring the tide back into synchronization with the Moon, and the Moon would no longer recede. Most of the dissipation occurs in a turbulent bottom boundary layer in shallow seas such as the European shelf around the British Isles, the Patagonian shelf off Argentina, and the Bering Sea. The dissipation of energy by tidal friction averages about 3.75 terawatts, of which 2.5 terawatts are from the principal M2 lunar component and the remainder from other components, both lunar and solar. An equilibrium tidal bulge does not really exist on Earth because the continents do not allow this mathematical solution to take place. Oceanic tides actually rotate around the ocean basins as vast gyres around several amphidromic points where no tide exists. The Moon pulls on each individual undulation as Earth rotates. Some undulations are ahead of the Moon, others are behind it, whereas still others are on either side. The bulges that actually do exist for the Moon to pull on are the net result of integrating the actual undulations over all the world's oceans. Earth's net equilibrium tide has an amplitude of only 3.23 centimeters, which is totally swamped by oceanic tides that can exceed 1 meter. Historical evidence this mechanism has been working for 4.5 billion years, since oceans first formed on Earth. There is geological and paleontological evidence that Earth rotated faster and that the Moon was closer to Earth in the remote past. Tidal rhythms are alternating layers of sand and silt laid down offshore from estuaries having great tidal flows. Daily, monthly, and seasonal cycles can be found in the deposits. This geological record is consistent with these conditions 620 million years ago. The day was 21.9 plus or minus 0.4 hours, and there were 13.1 plus or minus 0.1 synodic month per year and 400 plus or minus 7 solar days per year. The average recession rate of the Moon between then and now has been 2.17 plus or minus 0.31 centimeters per year, which is about half the present rate. Quantitative description of the Earth-Moon case. The motion of the Moon can be followed with an accuracy of a few centimeters by lunar laser ranging. Laser pulses are bounced off mirrors on the surface of the Moon, emplaced during the Apollo missions of 1969 to 1972 and by Lunokhod 2 in 1973. Measuring the return time of the pulse yields a very accurate measure of the distance. These measurements are fitted to the equations of motion. This yields numerical values for the Moon's secular deceleration, i.e. negative acceleration, in longitude and the rate of change of the semi-major axis of the Earth-Moon ellipse. For the period 1970 to 2012, the results are minus 25.82 plus or minus 0.03 arcsecond, Sentry 2 in ecliptic longitude, plus 38.08 plus or minus 0.04 millimeters year in the mean Earth-Moon distance. This is consistent with results from satellite laser ranging, a similar technique applied to artificial satellites orbiting Earth, which yields a model for the gravitational field of Earth, including that of the tides. The model accurately predicts the changes in the motion of the Moon. Finally, ancient observations of solar eclipses give fairly accurate positions for the Moon at those moments. Studies of these observations give results consistent with the value quoted above. The other consequence of tidal acceleration is the deceleration of the rotation of Earth. The rotation of Earth is somewhat erratic on all time scales due to various causes. The small tidal effect cannot be observed in a short period, but the cumulative effect on Earth's rotation as measured with a stable clock of a shortfall of even a few milliseconds every day becomes readily noticeable in a few centuries. Since some event in the remote past, more days and hours have passed than would be measured by stable clocks calibrated to the present, longer length of the day. This is known as delta-T. Recent values can be obtained from the International Earth Rotation and Reference System Service. A table of the actual length of the day in the past few centuries is also available. For the observed change in the Moon's orbit, the corresponding change in the length of the day can be computed. Plus 2.3 milliseconds century. However, from historical records over the past 2,700 years, the following average value is found. Plus 1.70 plus or minus 0.05 milliseconds century. The corresponding cumulative value is a parabola having a coefficient of T2 of delta T equals plus 3.1 century 2. Opposing the tidal deceleration of Earth is a mechanism that is in fact accelerating the rotation. Earth is not a sphere, but rather an ellipsoid that is flattened at the poles. SLR has shown that this flattening is decreasing. The explanation is that during the Ice Age large masses of ice collected at the poles and depressed the underlying rocks. The ice mass started disappearing over 10,000 years ago, but Earth's crust is still not in hydrostatic equilibrium and is still rebounding. As a consequence, the polar diameter of Earth increases, and because the mass and density remain the same, the volume remains the same. Therefore, the equatorial diameter is decreasing. As a consequence, mass moves closer to the rotation axis of Earth. This means that its moment of inertia is decreasing. Because its total angular momentum remains the same during this process, the rotation rate increases. This is the well-known phenomenon of a spinning figure skater who spins ever faster as she retracts her arms. For the observed change in the moment of inertia, the acceleration of rotation can be computed. The average value over the historical period must have been about minus 0.6 milliseconds century. This largely explains the historical observations. Other cases of tidal acceleration. Most natural satellites of the planets undergo tidal acceleration to some degree, except for the two classes of tidally decelerated bodies. In most cases, however, the effect is small enough that even after billions of years most satellites will not actually be lost. The effect is probably most pronounced for Mars's second moon Deimos, which may become an Earth-crossing asteroid after it leaks out of Mars's grip. The effect also arises between different components in a binary star. Tidal deceleration. This comes in two varieties.